Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Penn.
Welcome everybody again to another episode of our show. Today bringing another really awesome guest for you involved in areas of science and technology that are going to create a better tomorrow for all of us. Today on the show, we have the honor of being joined by Dr. Théau Peronnin, who is a physicist by training and a visionary leader in the field of quantum computing. Théau earned his master's degree from École Polytechnique in Paris, went on to complete a Ph.D. in quantum physics at ENS in Lyon, and embarked upon a mission to ultimately tackle what is considered one of the greatest technical challenges in the quantum computing field, and that is building truly fault-tolerant quantum computers. Dr. Peronnin co-founded the quantum computing startup Alice and Bob. They're based in Paris, but with really global ambitions. Took the helm as its CEO, and under the his leadership has focused on developing these really novel architectures known as cat qubits, which we'll get into in a little bit. These designs that ultimately embed error correction directly into the qubits, ultimately aiming to reduce the complexity of the hardware and error rates. Dr. Peronnin's work sits at the really interesting intersection of deep physics and engineering. He was part of academic research advancing superconducting qubit readout and control techniques, and has translated a lot of that research into momentum building infrastructure, labs, clean rooms, the cryogenic systems they require. And he frequently speaks on ultimately how quantum computing are not just going to accelerate algorithms that exist, but ultimately unlock new classes of problems in material science, in chemistry and biology, and even beyond that. Beyond technology, Dr. Peronnin emphasizes the importance of the ecosystem, the funding around quantum computing, and Audacity. Ultimately argues for Europe's importance in the intersection and the center of the industrial scaling and ambition of quantum computing and the quantum race. A lot to get into today. I'm really excited to have Dr. Théau Peronnin. Thank you so much for taking time to come on the show today.
Thank you for having me.
It's great having you, Théau. I look forward to getting into all these topics. Before we touch on anything quantum, though, would love to hand things over to you for a few minutes just to talk a little bit more about your background. I mean, in every paper I saw you've published to date, it's all quantum, with the exception of some project back in 2010 where you designed a magnetic cannon for an engineering Olympiad. What got you into physics to begin with, and a little bit of when you caught the quantum bug, if I could put it that way?
Yeah, if you go all the way back to 2010, I was in high school back then. So yeah, but that's actually when I got really into physics. Yeah, I was good in science in general, but I had the incredible chance to meet some young physicists back when I was in senior high school, who took the time to train me and some of my friends to take part in some very interesting physics competition that was not really an Olympiad that is sort of pen and paper, but really an experimental program where you have a whole year to set up experiments to answer some very open question like why are the edges of a coffee stain darker than the center of it? And through this very empirical research, I got to know better what is the real job of physicists. And what was really remarkable in that competition was the format of the actual competition that was called Physics Fight, which was really a debating tournament around physics problem, which is at the core of what you try to do when you're a physicist, which is to convince your peer that you have a new and interesting look onto an open question. And so, yeah, it's in high school that I got really into physics. At the time, I also had another quite academic passion that was for low-level electronics, really how you assemble transistors together to build some logic functions. But I realized pretty rapidly that I was coming 40 years too late to contribute meaningfully or to find some breakthroughs in that field. Too many extremely clever people had worked on that for quite a while. So I focused on physics. And when I entered École Polytechnique in 2012, it was just at the time where Serge Haroche and David Wineland got their Nobel Prize in quantum physics for manipulating individual photons or atoms in a quantum fashion. And it got me really excited because it was a whole new field where we're starting to have the level of control and technology that lets you start building machines. And back then, people were already starting to discuss the feasibility of a quantum computer. I remember vividly reading an IEEE Spectrum paper, news article about quantum computing back then, and thinking, well, this is a match made in heaven for me, because I can combine both of my passion in an entirely new field where we both test the fundamental of quantum physics and at the same time rebuild a computer much more powerful from the ground up with new rules. So this is how I started to steer my very early career towards quantum computing. First, more for a very academic based curiosity, and then later on because I met some incredible researchers, friends, and we had an angle on how to build that machine. Then it moved into a more industrial vision and ambition to actually build the system at scale, and the quest that led to Alice and Bob today.
Awesome. And before we get into the whole theme of fault tolerance and what you're doing with Cat Qubits and the company, I'd just like to again review for the audience, and we can just take a couple minutes on this, because we have sort of in broad terms discussed quantum computing in the past with some guests, but again, the basic we have, unlike traditional computers, where we have bits, we have these qubits, which take into account all these interesting properties, superposition that allows you to explore infinite states at once as opposed to just 0 or 1. The magic of entanglement, where certain states can tell other states what they're doing simultaneously, allows you to filter out wrong answers and reinforce right answers. Take us, if fault tolerance wasn't an issue, talk just a little bit about what a quantum computer is supposed to do potentially today, and then some of the problems that you think about. I mean, we've talked about quantum chemistry and biology on the show, not as much about cryptography and sort of finance systems and all that, but let's just review for the audience before we get into fault tolerance where we are today, and thinking what a quantum computer ultimately does for us today, if one was sitting right here.
It's an awesome question, because the answer is actually not trivial. The short answer is that we don't know. We don't know why our quantum computer is so powerful, or rather, should I say, we don't know what structure a problem must have to be easily addressable with a quantum computer, but not easily with a classical one. We know of basically two main families of use cases for which we have proven, before even the machine exists, that quantum computer will outperform extremely significantly classical computer, despite the fact that at a physical level, a quantum computer for the foreseeable future is going to be extremely slow compared to classical computers, meaning the clock speed of a quantum computer is at best in the megahertz range, whereas classical computers operate at several gigahertz. and extremely small, meaning the register, the memory, where the size of the problem of the inputs where we can tackle with a quantum computer is going to be at best in mega quantum bytes, more likely in kilo quantum bytes, which is millions, if not billions of times smaller than what classical computers can handle today. So for a quantum computer to outperform a classical one, it needs to have a very strong unfair advantage for the quantum one to succeed. And that comes from the fact that, indeed, as you mentioned, quantum computers have access to a slightly richer maths than classical ones. That is exemplified with the exotic properties of quantum mechanics, entanglement, teleportation, superposition, those kind of effects. But it's just a larger set of basic operation. And so for now, we found two main families for which we have an exponential speedup that compensate the quantum computer being smaller and slower, and actually vastly compensate that. The first one is the very, very large, very broad family of the many-body quantum physics problem, which is material science, chemistry, biology, nuclear physics. I mean, it's basically every time you're trying to understand nature, predict it, engineer it at a very low level, you need that. And so this one family of use case already vastly justifies building the machine. I mean, when you think about it, making chemistry and exact science is a fundamental change of engineering era for mankind. All of a sudden, you can start to play on the same ground as nature. I mean, when you think of one of your living cell, you have so many wonderful molecular machines, ion pump that pumps ion in and out of the cell, walking robots that walk along your cytoskeleton, so many of those machines. But we're absolutely clueless as humans when it comes to engineering such systems, such molecular systems. And this is the kind of thing that quantum computers will eventually enable. So that's the first family. The second one is really history repeating itself. And the first computers were, boosted by the imitation game movie, the ability of breaking Enigma's code with the first computers and Turing's adventure in that. And so indeed, at the moment, a lot of the traction around quantum comes from the fact that it's also a code-breaking machine for RSA and elliptic curve. So basically internet and Bitcoin, if you want.
Sure.
But that is eventually a marginal use case. What really gets me extremely excited is the first one, the ability to change our engineering era. But maybe to wrap up, what is absolutely formidable with quantum is that we already know of those use cases even before the machine being here at scale, delivering their promises. And so the acceptance bar at the moment for a use case is extremely high, meaning you need to be able to prove on pen and paper through rigorous math that your machine will be able to do something classical computers cannot do. If we had the same level of constraint for classical computing, you'd never had any neural network. Because at the moment in AI, we have absolutely no proofs, no understanding on why do neural networks learn so efficiently and scale the way they scale. This is entirely rigorous but empirical science. And so I'm really excited also about what people will discover when tinkering around with our machines that are coming in just a few years.
Excellent. And now, making the transition to, the world of fault-tolerant architectures, which is where you've spent a lot of time now the last several years. And again, just for the audience, and I don't want to skewer this, but this principle of coherence in a quantum computer between the different qubits and the ultimate, ability for this quantum magic to happen has to happen in a very delicate environment, and things like heat and vibration and other fields and all that sorts of that stuff can interfere with that. And I guess today, in today's world where, and people can look up who else is building quantum computers, but the current offerings, let's say, that are out there are what are known as NISQ, noisy intermediate scale quantum devices. And again, in just doing some basic research about this concept, there's these theorems about what a proper level of tolerance should be, and these different ways that I guess existing companies have been trying to build in error correction over the last several years in terms of the gates and sort of other surface code. I was wondering, again, if you could take a little time just to walk us through sort of what the existing NISQ domain is all about and sort of what previous concepts in error correction have been, and then we'll transition into sort of the work you did in your dissertation and into the company.
Awesome. So, yeah, I think first we need to take a small step back, which
Sure.
is to understand why is it so hard to build a quantum computer. And it really boils down to the fact that a quantum computer, building a quantum computer at its core is a complete paradox. Meaning, on one hand, you want a machine, some hardware, to behave quantum mechanically. And for that, if you think of the Schrödinger cat's box
Yep.
thought experiment, your system needs to be perfectly isolated from the rest of the world, really decoupled from the rest of the universe, meaning no information whatsoever, whether it's one molecule, one vibration, as you mentioned, whatever types of information should get out of your quantum system. And if some gets out, that creates decoherence. It's really nature projecting, opening the box and picking one outcome,
Right.
the collapse of the wave function. Now, at the same time, so that's you need to isolate, but at the same time, you're trying to build a computer, a machine you can program, input data, output results. And all of a sudden, you can feel that the two things are contradictory. And actually, you find systems in nature that are good at either one of them, but never both. So, for example, you can manipulate the spins of a nuclei of an atom. Those are extremely well isolated quantum systems, but then they're extremely hard to control because they're extremely well isolated. And so you're off. On the other end of the spectrum, you find many degrees of freedom, many systems that you can control easily, but that are extremely hard to maintain in a quantum state.
Mm-hmm.
So to put that into figures, when you try to build a quantum system today, whatever the modality, whether you're controlling individual atoms with laser or like us using superconducting circuits operating in the gigahertz range, cooled down at very low temperature, whatever the modality, you typically end up making errors every 1,000 or 100 operation per quantum bit. Meaning 10 to the minus 2, 10 to the minus 3, at best, on the very best system, 10 to the minus 4. So one every 10,000 operation. Now, when you look at the use cases I mentioned before, the level of reliability of remaining error rates you need to achieve is a billion times better, or at least 1,000,000 times for the first use cases. And so you can already see the challenge. That means that it's been, 25, 30 years physicists have been trying to improve quantum system, quantum engineering. We're not going to find, all of a sudden, a wonder material that behaves 1,000,000 times better than everything we tried before. Maybe we'll gain 1 order of magnitude, maybe 2, but that's about it. So you need something else. And you also need to find some utility for what you're going to build in the meantime. So those are the two answers to your question. So how we're going to solve this millionfold improvement in error rate is through quantum error correction. And I'm going to tell you all about it in a minute. But before, the thing you need to know about quantum error correction is that it's all about redundancy. And so it's building extremely large system and using most of it as redundancy to correct for errors as they go. So the third generation of industrial players fully aware of that fact, said, okay, on our way to building those large systems, we're building prototypes, early stage system, and we know asymptotically they're going to be extremely powerful once they're fault tolerant. We know classical computers can do stuff, but it's still an open question what can semi-quantum or noisy intermediate scale quantum system can do. And so the current offerings are really all about that. It's saying, well, we have no algorithmic proofs of utility of those systems, but maybe there is some utility in there. We don't know. And it's interesting research platform. From that, the community has taken two main takeaways. The first one, and that's the most important one, is that there is no funky business happening with quantum at scale. Meaning, for a while, until very recently, you could find physicists arguing that, well, quantum mechanics doesn't hold, holds only up to a certain system size. At some point, it has to become classical one way or another because big things are classical and small things are quantum. So there must be a critical size in between. This is wrong. Quantum mechanics happens exactly as we think, as long as it is well isolated. And that is already the first takeaway of the quantum supremacy experiments. The second takeaway is that those noisy intermediate scale systems are already interesting to serve as placeholders, as test bench, so that we can start building, we as a community, not necessarily Alice and Bob, as we are focused on fault tolerant, but we can start developing use cases, applications, and start preparing for the arrival of those large-scale fault-tolerant systems. So this is why people have been toying around. Now, I'd say since a year or so, most serious players in the quantum race are now solely focused on the race towards fault-tolerant quantum system, because noisy intermediate scale systems are falling short of the whole promises of quantum. And every vendor's roadmap converge around 2030 to delivering the first large-scale fault-tolerant quantum system. Now, every vendor, every approach, every modality has its pros and cons. And so the idea of fault tolerance, as I mentioned before, is really about redundancy. And that's not restricted to quantum. I mean, you have error correction everywhere in your classical world. Every telecommunication, this call we're having today, requires a lot of error correction through the communication channels, and so redundancy to compensate for the noise, the losses of the signal. And actually, in your IBAN or, in many other things in everyday's life, you'll find error correction. A QR code, for example, is all about error correction also. So those are good examples. Now, in quantum, it's slightly more complex because we have more errors to correct in volume, but also in diversity. We don't have only one type of errors, but two. We have the classical error, the bit flip that switches 0 into a 1 and vice versa. But we also have a purely quantum error, the phase flip that switches a superposed state 0 plus 1 into 0 minus 1. So two types of errors, a lot of them happening. And so when you run the numbers, the level of redundancy you require with the standard approach is typically on the order of 1,000 to 1 to get to sufficiently low error rate. Meaning you need 1,000 physical quantum bit per sufficiently good logical qubit. Meaning the quantum bit of the software developer, the one who completely forgets about the specifics of the hardware. And that makes the whole quest extremely challenging. Say you want to break RSA 2048, so the internet security, with the standard approach, with those numbers, you need 20 million physical qubits to do that. Those are systems that would cost billions of dollars and require tremendous size with today's enabling technology. So it seems quite unrealistic, but at the core of that algorithm, you only need 6,000 logical qubits. So all of the challenge of building a quantum computer is making error correction efficient. And this is really the raison d'être, the purpose of Alice and Bob is to find more clever ways to do so. So yeah, that's how we came to designing the cat qubit, building in the error correction directly within the qubit to dramatically simplify that.
And I mean, this is also, and in sort of your work in thinking about the redundancy and making error correction efficient, I'd like to just, and again, I'll let you run with this before again we jump into Alice and Bob. But 2020, you publish your dissertation entitled "Building and Operating a Quantum Node of a Microwave Network," and let's just say you really, when I say, you put together a really comprehensive blueprint here, everything from the cryogenics to cool terms like dielectric losses and residual thermal photons and everything in between that ultimately reduce the hurdles in getting to this thing which called a microwave quantum node. Now, again, I'd like you to, because I believe that a lot of this work ultimately lays the groundwork for Alice and Bob, but could you talk for just a little bit about your dissertation here? Because it's very, I took, dove into it a little bit, but can you really talk through a little bit of what a microwave quantum node is all about and where we're headed here? Because it's a little red, but I'd love to hear about it.
Yeah, my dissertation is only part of the story. You need my co-founder's Ph.D. Also to better understand. So my co-founder, Raphael Lescan, and now CTO of Alice and Bob, really worked on the core idea that we're now leveraging, which is how do you actually build cat qubits? But my PhD, which was in really tight relationship, I contributed to the 2020 Nature Physics paper we published with Raphael on cat qubits. During my PhD, I built a more versatile platform, which we titled a quantum node, and then led to quite a few different papers. I think what was at the heart of that work was really trying to find a core building block, a quantum node, that has access to all the tools that quantum mechanics gives us in what kind of quantum states we can prepare, handle, control, and be a great test bench for encodings and efficient way to interconnect qubit, to correct for errors, to do all the science we're now doing at Alice and Bob, which is how do you engineer microwave circuits, really something that is just classical non-linear physics, in a way that when it's become cold and quantum, you have access to a great level of engineering. What we do at Alice and Bob, and I don't want to be too technical, is called Hamiltonian engineering. It's really how do we engineer the circuit of the parameters of the circuit, so that we can control quantum mechanics in a very clever way to to engineer a quantum system the same way you'd engineer a classical system. And that actually has roots in more of the previous generation, that of my PhD advisor and his colleagues, which was trying to combine the science of classical automation, how you can take the equation of motion of a classical system and say, this is a controllable system in a mathematical way. I can engineer it to have this and that properties, and apply that science to the equation of quantum mechanics, the Schrödinger equation. If you want to keep it simple, it's rather the Lindblad one, but yeah. And it's... and that gave birth to the cat qubit, which is one of the outcome of that broader field of engineering Hamiltonians to design clever ways. And just to give you an idea of the shift of paradigm we introduced through that, I told you earlier that for a system to behave quantum mechanically, it needs to be perfectly isolated from the rest of the world. Sure. And this is how everyone else is trying to build quantum computers today. We, thanks to the insights of that science that we're pioneering, we took a slightly different route. We found a way to continuously inject energy to compensate for losses in the system, constantly extract entropy, cool it down, correct for errors, without extracting any information from the system, meaning without creating any decoherence. And so it used to be very mind-bending for our peers to say, well, you're trying to build a quantum system in an extremely open way, in a way that exchange constantly energy with its environment, because we found a way to hide the information so that it does not create decoherence. So yeah, all those ideas were already there during both our PhDs with Raphael from 2016 to 2020. And because we were in very small, by the size, not the impact, but very small academic groups, we had, both of us, to do every single step of the process. So everything from the design of the experiment, all the theory, the maths, but also the groundwork. How do you manufacture the chip? We built our own chips ourselves. The whole setup of the experiment, how you control your electronics, how you write low-level code. So when we started the company, we had a good overview of how incredibly difficult it was going to be, and all the different fields of engineering we needed to assemble together to make the whole thing come true. And now we're really at the stage where it's becoming very exciting, because we're now more than 150. We're starting to have large plants. We're building a somewhat very industrial facility north of Paris. So yeah, it's really fun to see those ideas from a PhD become a large industrial thing just a few years later.
Mm-hmm. Mm-hmm. And if we just sort of to lay out the because you mentioned the cat qubit, which is obviously core to what Alice and Bob is all about, and sort of I've seen it defined as a bosonic qubit versus so there's transmon qubits and trapped ion qubits and photonic qubits. And again, you were if again, can you just take us for a few minutes through that model specifically, because again, you as you've been saying, you took your magic of your PhD and your co-founders put together something here that again has built-in error protection, works with this superconducting resonating concept. Again, if you could sort of just say a few more words about cat qubits and in comparison to other types of qubits, that would be cool as well.
Yeah, the first thing you need to know, and I really want the audience to know that very clearly, is that cat qubits are superconducting qubits. I mean, from the outside, you could not tell, except from the colors of the system, that this is an Alice and Bob quantum computer and not an IBM or Google or whoever else does superconducting qubits. We operate in the gigahertz range at cryogenic temperature, controlled through classical electronics. Now, what changed is the layout of the chip. What do we design on the chip? How do we assemble the individual component, the capacitors, the inductors, the Josephson junctions, together to build slightly different circuits from the standard qubit, superconducting qubit called the Transmon, as you mentioned, which is the most simple, most elementary, actually, qubit you can think of. It's just a capacitor and one junction. And so you really can't make anything more simple than that. And what we do is a slightly more elaborate circuit, actually 2 times more complex. So you have every component twice. And what that circuit does is that it constantly exchange photons, I mean microwave photons, so microwave gigahertz excitation, with environment, but by pairs, 2 by 2. And what is really, really great with that system is that actually it has a perfect mechanical analogy. You can try this at home, actually. The equation of motion are exactly identical with a pendulum that you would excite vertically at twice its frequency. You can try that. You take a string, you attach some weight at the bottom, and you drive it vertically at twice its natural frequency. Okay. And what you would see is that you have two stable positions of same amplitude but opposite phase. And you can already guess that from just the symmetry of the problem, because you're driving it vertically, it has a mirror symmetry. But what is really remarkable is that your hand or your drive or the environment has no way to distinguish those two different phases. It has the same amplitude, and from the point of view of the environment, it does not have access to information about whether it's one or the other. And so what we're doing on the electrical circuit is exactly that. The fact that you're driving at twice the frequency becomes a square in the equation, which means that you're exchanging photons 2 by 2, as I mentioned before. And instead of being a pendulum, it's an LC resonator, harmonic oscillator, so inductance, capacitance. And the way we create the nonlinearity of the cosine of your pendulum that is required for this to work, what is just through the nonlinearity of the Joseph function. But just to wrap up, it's a circuit, just like other superconducting circuit, slightly more complex in the design, 2 times actually, but that has a built-in stabilization mechanism. And what that mechanism leads to is an exponential suppression of one of the 2 types of errors at a linear cost on the other. Meaning, when you crank up the power, when you increase the number of photons, microwave photons you're sending to your device, or just crank up the power if you want, the typical time between 2 bit flip errors increases exponentially. And so we now have, I believe by quite a bit, the world record of bit flip time, more than an hour in our system. So we're kind of good to go. We solved by design one of the 2 main source of errors in the quantum computer. Now we're left with the other error, the phase flip, which we have slightly more, actually linearly more than our competitors, but that is entirely compensated for by the fact that now that we only have one type of errors to correct, we can use much simpler codes, error correction code. Actually, we can use classical error correction codes, because correcting just one error is the classical case of error correction. And when you run the numbers on a use case, what you end up showing is that eventually, through this combination of using simpler codes, more efficient codes, and having a first layer of built-in error correction, you reduce the total overhead of the system by up to 200-fold. So meaning, instead of requiring 20 million physical qubits to break RSA 2048, we're down to slightly below 100,000. So it's not just the timeline or the complexity, it's also directly the cost of the system that we slashed by 200-fold. And this is the kind of things that get us excited at the moment, is really the ability to continuously improve the architecture, the concepts of error correction, to make the whole thing way more plausible and much easier to achieve. And this is how our roadmap targets a system by 2030 that we nicknamed Graphene, that will be the first really impactful quantum computer with 100 logical qubits at 10 to the minus 6 error rate that requires only 2,000 cats, 2,000 physical qubits to be made. And that is a system that fits within today's enabling technology. And actually, the industrial plant I mentioned before that we're currently building and that will be live in a few months is where we're starting to build this graphene system over the next few years. So it's coming in fast thanks to those savings and the fact that we're not done improving the architecture. Just last summer, where we published a new paper on some obscure technical topics called magic state distillation. I'll spare you the detail, but basically we shrunk by 10x, 1/4 of the whole chip. So 1/4 shrunk by 10x, but it's just a continuous improvement cycle through more clever maths and better engineering.
Mm-hmm. And again, I've done several guests on the show the last couple of years, Théau, in sort of the area of fusion energy, and I see a lot of interesting parallels there in the sense, we're at this very interesting inflection point where we've been spending time in that area with plasmas, but the whole sort of holy grail for burning sustainable plasmas has gotten a lot closer with these new technologies. Obviously, with where you're going in quantum computing, I mean, things are really taking off. Could you just, again, and nothing confidential, of course, because you probably have a lot of stuff in development between now. I mean, I'll accept right now. You solved all the error correction stuff, and we have a fault tolerant model. What happens between now and this 2030 date that you're talking about? Can you say a couple of the other important pieces of the Holy Grail that need to fall in place? Is everything in place with whoever you're going to be partnering with? What should be on the lookout 2027, 2028, and so forth as this then proceeds after you have your factory up and going?
The first thing you need to know is that when you're building frontier hardware, 4 years is tomorrow. So for us, we're already in that program. I mean, some of the equipment, some of the machines we're buying to build our machine have lead time of 18 months or things like that. So, but more generally, the whole field moved away from being basic science to entering what engineers called integration hell. Which is you have a beautiful idea, you demonstrated a small component, and you start to assemble the system at scale, and all of a sudden nothing works. And you enter this cycle of hardware debugging of all the parts of your system, and that requires a tremendous amount of engineering legwork. It's about validating every single component of those large-scale systems, improving the yield of the manufacturing, those kind of things that are, proper engineering challenges, but no longer about the fundamentals, no longer about the physics. And contrary to fusion, at least in our roadmap, it's not about finding better materials. The numbers of each individual component are sufficiently good to go to that graphene system by 2030. Now it's maintaining those level of performances at scale. That is the main challenge. And so to illustrate that, it's just like when you can design a rocket with 5 physicists in a garage and access to internet to get the value of each materials. But the minute you want to actually build the whole rocket and send it into space, all of a sudden you need hundreds, if not thousands, of engineers to test and assemble all those components. So that's exactly the era we're in at the moment. And so everything we're doing on the way to 2030 is just increasing the size of our prototypes. So currently we're working on a chip called Helium, made out of 12 cat qubits. Next year we'll move on to lithium 48, then we'll have beryllium 250, and finally graphene at 2000 cats, making 100 logical qubit together. So yeah, it's a scaling phase, and a lot of momentum, at least on our platform. I think you need to invite some of my competitors to have a better idea of their challenges. But yeah, it's different, and so I invite the listeners or the viewers to not be shy. There is room for everyone to contribute. We need so many different types of engineers. We're building a lot of software to both for our internal tooling suite, but also more generally for the firmware of the quantum computer. We have microwave engineers, mechanical engineers, nanofabrication. We now have a lot of machine learning. Not that I want to say AI for the sake of AI, but just we're doing physics in 2025, that's part of your toolbox. And this is why we have that partnership with NVIDIA as well. So yeah, room for everyone to contribute here.
Well, your investors definitely are happy. You've raised over 130 million euros. 150 plus employees, and as you know, you were just talking about the sort of the quantum ecosystem there. And I mentioned at the beginning of the show that you're passionate about making sure that Europe is a major part of the quantum race. Could you just say a couple words about sort of the general quantum environment? I mean, obviously you're in Paris, but you have global aspirations. Thoughts on how the quantum ecosystem is developing in France and the surrounding countries, and I guess what you would like to see in terms of sort of the future of whether that's public private investment in this space. Anything else on that front that you could tell us about?
Yeah, I mean it's extremely exciting. And I, I mean, it's a once in a lifetime opportunity. You don't have that many fundamental breakthroughs in science and engineering that come with so many things that could be unlocked by the system that are such at the frontier of both physics, engineering. I mean the type of real time computing we need to do on FPGA boards is really remarkable. You have so many interesting engineering challenges at the frontier of science in a global race to make that machines in a very short time frame. I mean, 4 years is tomorrow. That the whole field is boiling at the moment. And if you look at the publicly traded companies like IonQ or Rigetti, you can see the level of excitement of the field is just getting started. And I think over the last year, the valuation went 10x, exactly because of the global pressure towards quantum. So that is extremely exciting in terms of the intensity of that race, the number of things that remains completely open in terms of room for discoveries or clever ideas. And we're just building the hardware. Tomorrow it will be all about the quantum ecosystem in terms of software and applications. And here it's just burgeoning. So yeah, a lot of excitement. Unfortunately, because this is the world we live in, there is a bit of geopolitics, and hence I guess your question about Europe. I think in France it's a bit peculiar. You know, where we're really bad at training masses in math, but we're really good at training a small elite in maths. So we're in France, so we're really well equipped when it comes to those kind of challenges. One example of that is the fact that over the last 13 years there were 3 Nobel Prizes awarded to quantum physics. Each time there was a French guy in it. 2012, Serge Haroche, 2022, Alain Aspect, and this year, Michel Devoret.
Yep.
And actually, we are grandchildren of Michel Devoret's work here directly. He advised the company in its early days before joining Google. So yeah, it's extremely exciting. We're seeing a lot of capital starting to being deployed in quantum. So an increasing amount of resources, more and more procurement. So business happening, especially on the public side, just like in the early days of classical computing, or just like in space. Governments are playing a heavy role in making sure this industry thrives, and that is very exciting. So yeah, it's very interesting, and I think now that the ecosystem is starting to sort of clarify itself with the major players, the Magnificent Seven, NVIDIA and companies, investing more and more into quantum, and just a small leadership of 10, 15 startups that are competing at the top level to get there. Yeah, it's the perfect time to join this ecosystem.
Yeah, I mean, I'm excited for you. I mean, I think the next couple of years are going to be super fun with where you are and what you're building. And I look for, coming out of the pharmaceutical industry, I look forward to sort of all the chemical and biological applications. And it's going to be, really fascinating to ultimately unlock these problems with the systems you're developing, and have new solutions for, whether it's health, whether it's agriculture, energy. But I look forward to continue to follow your work, Théau. Again, for everybody that's going to be listening to this show, across the various podcast networks, or who will be watching on the YouTube channel. You've been listening to Dr. Théau Peronnin, Chief Executive Officer, Allison Bob, doing really amazing work to build truly fault-tolerant quantum computers to solve all sorts of problems for us. Théau, again, I want to thank you for taking the time out of your schedule to come talk to us for a while, to distill down some really complex themes for us. Obviously, thank you for everything you do there at Allison Bob and making this a reality. And as we like to say on our show, thanks for helping to create a better tomorrow through the type of science and technology you're championing. But it's really an awesome story, and I wish you and the team the best with it all as you move forward.
Thanks, Ira.
Great having you.